Welcome back to Differential Calculus. In this video, I want to introduce you to the idea of an accumulation function. Mathematically, the definition of an accumulation function is a function capital F of x defined by the integral from some starting point. It can actually be any starting point you would like, but 0 is a common choice, up to the point x. That's a little bit weird. Variable as one of the limits of integration. But then we're going to integrate some other function, little f. And I can't call it little f of x because x already has a meaning in the integral. So I need some other variable. Sometimes you'll use t, sometimes you'll use the Greek letter tau, or really anything will work. All right, so that is called a dummy variable. Its only purpose is to be the thing that you are integrating over so that you can use x to define the limit of integration. And if I jump over to Desmos and we think about this analytically, the white graph here, the function that I've graphed, is the function little f of x. And the integral is going to ask us about the area under the curve. So if I move my slider over a little bit here, I can step away from the picture instead of towards it. Sorry about that. Right? I can think about the integral is the area under the curve. It's over here. The area under the curve. And as we move this, we're going to change the area. That will change the value of the function. All right, so we pick our value of x, we calculate the area up to that point, and that's the value of the function big F of x. All right. We're calling a function defined this way an accumulation function. And the function inside the integral little f is generally called the density function. Although honestly, the vocabulary here doesn't matter that much, but I did want to at least mention it because density function is kind of the heart of what we're doing and why we're doing it. The easiest interpretation of this sort of a situation is mass and density. If you have an object, say a solid rod, that has different densities along the rod, and you define a function to determine the density at a particular point. For example, if you have a cement rod that is filled with foam aggregate, as you poured the rod, the aggregate may have floated to the top. So if you poured it in a vertical sense, at the top there is more foam and less cement. The density is lighter. At the bottom there is more cement and less foam. The density is higher. The mass is going to be the density times the volume, and the volume will change based on how much of a selection of this that you're going to be taking. So setting up an integral like this will give you the mass of a certain amount of the object. We'll be using several examples related to that in future courses, but for right now, just that basic idea is where I want you to be. There's, of course, nothing special about mass in a density accumulation function. One of the other common applications of this is in probability. So if I jump back over to Desmos, you might, if you've taken a course in statistics in the past, recognize this function. This is the graph of the Gaussian normal curve. And you might remember from a statistics course, finding a z-score and then looking up on a table the area under the curve to the left of that z-score. Well, those tables are created by someone doing calculus. It turns out that there's an equation for this curve. It's a nasty equation and it's beyond the scope of this course, but if you continue far enough in calculus, generally in Calc 3, I try to use this as one of the examples. We develop the tools to be able to actually perform this integral. But we have a function, we can evaluate the integral at various points and populate a table with all of those values so that people can look it up without having to be able to do the integral. But it's just an integral of an accumulation function. Excuse me. All right. So those are the basic ideas. That's what I want you to think about when you think about an accumulation function. Let's jump back to that first graph we were looking at. And here I want to think about things a little bit differently. I want to think about how is this function changing, right? If I think about the area under the curve, if I go to the next x value, I add to the curve this little bit of area, right? I can't twist my wrist so that you can actually see that I'm holding my fingers apart, right? I have a little bit of a space here, dx, and the height of the bar is the value of the function. So when I add a little bit on to the region, a little dx added to the area, I can use that to figure out what's going on here. So I'm going to try to redraw that graph. It is not going to come out well, but that's okay. All right, so we have something that looks kind of like that. We have our little space dx here. And the height of this is little f of x. And the area here is big F of x. And so the conclusion I'm coming to is that a small change in the total area with respect to x has to be equal to the value of the little function. But wait a second. Remembering what big F is, I am now claiming that the derivative of the integral from 0 to x of my function f of, I need a dummy variable, so f of tau d tau, is equal to f of x. When you take the derivative of the integral of a function, the derivative and integral cancel each other out, leaving you with that function. This is a big deal. This is a huge deal. This is what ties the entire course of calculus together. And so since it is such a big deal, it gets a big name. This is the fundamental theorem of calculus. You may not, there we go. You may or may not have heard them referred to as fundamental theorems, but there are two fundamental theorems that you've come across in previous courses. I want to remind you of them to try to underscore just how big of a deal the fundamental theorem is to the study of calculus. The fundamental theorem of arithmetic tells us that every whole number can be written uniquely as the product of prime numbers up to commutativity. So if I have a number like 24, you hopefully have some recollection of an arithmetic class where you factored 24 into something like 6 times 4. You factored 6 as 2 times 3. You factored 4 as 2 times 2. And you said, okay, 24 has a prime factorization of 2 times 3 times 2 times 2. Although you then probably used the commutative property of multiplication to rewrite this as 2 times 2 times 2 times 3, or 2 cubed times 3, right? All of those are the same product. It's the same numbers, just shuffling the order. That's what we mean when we say up to commutativity. But this is fundamental to arithmetic, right? This was step one in looking for greatest common factor or least common multiple, which you then used to reduce fractions, to find common denominators, to add or subtract fractions, to compare fractions. Everything about fractions relied on being able to find a prime factorization and knowing that the prime factorization was unique. So that is the fundamental theorem of arithmetic. There is also, get my head back out of the way, a fundamental theorem of equations. This used to be called the fundamental theorem of algebra, but in the past 100 years or so, the topic of algebra has become a lot more broad than the algebra you learn in high school algebra 1 and 2 and in college algebra. Regardless, the fundamental theorem of equations says that a polynomial equation of degree n has exactly n not necessarily distinct roots. This is why you know that if you start with an equation like x squared minus 4 equals 0, before you start, this is a second degree equation, so you know it will have two solutions. We factor this to x plus 2 times x minus 2 equals 0, and then we use the zero product rule to say that either x plus 2 is equal to 0 or x minus 2 is equal to 0, which means that x is negative 2 or x is positive 2. A slightly different equation, x squared minus 4x plus 4 equals 0. Again, second degree equation, so we know it has two roots. We factor, this one factors into x minus 2 times x minus 2. Which gives us that x minus 2 is equal to 0, or x minus 2 is equal to 0, which in turn means that x is 2, or x is 2. You get the same root in both cases. We call that case a multiplicity. Right? The root is a repeated root. That's why the fundamental theorem says that the roots don't necessarily have to be distinct. And that is what you do in high school algebra and college algebra. You look at an algebraic equation. A linear equation is a degree 1, it has exactly one solution. A quadratic equation is degree 2, it has exactly two solutions. If you have a larger polynomial equation, you'll have more solutions. If you have a rational or a radical equation, you're going to rewrite it as a polynomial equation, and you're going to know that it has exactly n roots. So you can solve all of these equations, and it all comes down to this fundamental theorem of equations to tell you how many solutions to expect to find. Right? That is the level at which the fundamental theorem of calculus is trying to live up to. In the next video, I'm going to show you how that works, why that works, but for right now, let's just take a look at a relatively simple example. I'm going to define an accumulation function, big F of x, as the integral from 0 to x of tau d tau. This is a fairly straightforward situation. I can think about this graphically. I know the graph of x, y equals x, looks like that. And if I pick out a particular x value, I know that my y value is also x. The function is the area under the curve. The curve is a triangle. It is a right triangle with length and width both x. So the area here is going to be 1/2 times x times x. And the area is the value of the accumulation function. So if my density function f of x equals x, then my accumulation function big F of x is equal to 1/2 x squared. And we can check the fundamental theorem of calculus. The fundamental theorem of calculus says that if I take the derivative of 1/2 x squared, well, the derivative of x squared is 2x. Multiply that by 1/2 and you get x. And we can see that, yes, that is exactly the value of the density function we started with. Using the same sort of geometric argument, I would like you to consider the density function f of x is 4x. And the accumulation function, the integral from 0 to x of 4 tau d tau. Right. If you've studied calculus before, or even if you just watched the next video in this series, you will know that there are analytic tools that let you solve this equation very easily. But I'd like you to use the geometric reasoning that I just used in that last problem. Graph this, recognize the shape, write an expression for the area under the curve, and realize that that is the accumulation function. Once you have the accumulation function, take the derivative of the accumulation function and check to make sure that you end up with the density function that we started with. All right, take a couple of minutes to play around with that, and I'll see you in the next video.